Before we wrap this up, let's actually also look at the CLI. So the command line interface, so I'm opening up CLI.js, right? And let me just map a keystroke here in Vim to run node on CLI.js, or to run CLI.js through node. So if I just hit that, we're running this. And again, you can see this works fine. And actually, I mean, this is a pretty short implementation as well. So the game loop is a bit different here. We still do this sort of showing and stepping, but what I do is I set an interval. Yeah, so what we do is we make use of set interval, right? Which is this function in JavaScript that calls a function with a regular interval. And it's also expressed in milliseconds, but here actually I run it every 80 milliseconds. So yeah, for some odd reason, I chose a different interval for the terminal application. Maybe we should change this to 100 in order to sort of make it have the same speed, but never mind. I mean, that we can trivially change. But essentially what this set interval does is that it does these two things, right? We pass a function to set interval that first calls step and then calls show. And actually, I mean, now that I think about it, what we could have done is we could have said pipe step and then show, like so, over 80. And that should be the same. That should be the same thing, right? And actually that didn't work, and I think it has something to do with like the console log here or something like that, so like the context disappears. But never mind, let's not think about that now. And either way, I mean, piping here is not necessarily a sensible thing to do, because step and show are mutating functions, or there are functions that like, I mean, compose and pipe we usually use when we actually want to pipe or compose functions, like because we're actually passing data through. Now we're just saying do this thing and then do that thing, so like never mind. But anyway, so set interval, what it does is that it calls step and then it calls show, and it does that every 80 milliseconds. And what show does, let's start with the show, right? So both of these, both show and step, are functions that don't take any arguments. And show, what it does is that it console logs this strange character, which works as a clearing, right? Like if you think about it, actually if I remove this, I think that would be the most simple way of describing this. Like if we remove this and then redraw, you can see that the game works, right? But if I scroll out, you can see we have multiple versions of the game, where the lower one, this one here in the bottom, this one is the active one, because that's the freshest one. The other ones are histories, and actually we are printing and printing and printing, and so it's not like, it looks static, but it's not actually static. I mean, it's like a moving, like these old animated movies, like where you draw, where you pull past a strip of multiple images, and that's actually exactly what happens now. Like this is a strip of multiple images. Anyway, sorry, let's stop thinking about that now. It's pretty interesting. But if we add that character, we keep clearing the screen all the time, so that we're just, it's like clearing the canvas. So that's the first part of show, like we clear. And then what we do is that we have these functions on the object matrix, right? So here you can see we have a comment that says matrix operations, and then following that there's a constant called matrix, which is sort of a module with a bunch of functions that operates on matrices. And actually, I mean, I use the word matrix here indicatively, like it's not actually truly a matrix, but what we have is that we have an array of an array, like we have a two-dimensional array, where I think first I do rows and then I do columns, or maybe the other way around. So anyway, the things under the matrix module are then things that operate on this type of structure. So what we do is essentially then that we say, okay, matrix.toString of matrix.fromState given the current state. So here we probably could actually use pipe in a sensible manner. So what we're doing is that we're saying, yeah, pipe matrix from state and then matrix to string, and we're piping that through the state. So this is probably the reason why I didn't do this, because the line turned out to be longer. Like if you compare the two lines, this is actually longer, but that should work fine as well. And like if we run that, that doesn't work fine. Oh, sorry, my bad. This is probably why the other thing didn't work as well. We're not using array syntax. I should pipe like that. Yeah, sorry, so that's probably why the other thing didn't work as well. Maybe didn't have anything to do with the console log. But anyways, so yeah, we could use a pipe there instead. But as just said, I mean, even if I remove that sort of array here, you can see that this line is longer, and I just figured, never mind, let's just do this. But anyways, both of these things are equivalent. But yeah, maybe this one is more clear, so maybe let's keep that one. I guess I didn't because of the length of the lines. Like you can see, we're at 88. We're at column 88. state. But anyways, let's keep it like that for now. So that's show. So what it does is essentially it clears the screen. It says construct a matrix from the current state. Remember, the state is the same kind of state that we used in the web GUI, right? Like, that's what we're saying. Like, we use the same state tree, but we do different things based on this state tree, and thus we can show a command line interface and we can show a web interface. So from this current state, we produce a matrix, and then we take that matrix and we pass it to two strings. So what we do is that we produce the matrix, and then immediately we turn that matrix into a string. So actually, I mean, maybe you could argue that I've made it unnecessarily complicated in some way, and maybe we should find a way which is more similar to the web approach, where we sort of just immediately do or display what we want to display. But to me, this seemed like the easiest approach, like having this intermediate data structure that's this matrix-like thing. Because I mean, if you think about it, we print this pretty much as a matrix, right? Like this has a number of rows and it has a number of columns. And actually, if we look at toString here in the matrix module, you can see that this is where it becomes obvious that it's fairly trivial, because toString takes, I wrote XSX here because, like, usually in functional programming you will see people say like XS or SS or something like that to indicate that you have an array of something. So you have an array of X's here. But I tend to write XSXs. I'm not sure if that's conventional. I hope that's conventional because it seems sensible to indicate that it's an array of X's. So, and that's why I say XSXs here on the outside and then X's here on the inside. So the way this works is that we map over the outer array, and then for every inner array we join up all of the values with a space. If you think about it, you can see here that there's a space in between. There's a space in between all of the different dots. Like if we didn't have that space, probably this won't, yeah, this actually does work, right? This doesn't look very nice, also because columns are a lot narrower than the rows. So we need that extra space in order to sort of make it look a bit more nice. So we join it up with space, and then we join up each of these rows with a \r\n, which is essentially a line break, so that we can print it as a single string that sort of looks like a grid. And actually, I just realized I used to have a point-free, or not a point-free version of this, but rather a version that's more similar to the make function here, where instead of actually calling map on the axis of x's, we say map and pass the axis of x's, because I guess that could be more elegant than this. But anyways, there are multiple ways you can rewrite this function, and some of them are probably a lot more elegant than the way I've written it now. But anyways, that's the toString function. And of course, if we think about this method again, like what we were saying is that we first do from state and then we do toString. So we start with this from state and then we do toString. So from state, what that does is that it creates one of these axis of x's. It creates one of these grids or one of these matrices containing the appropriate values. And how we do that is essentially by piping, right? We say, well, we need to pass this state, so we take the state as an argument and then we pipe it through a few functions. But the first function makes the matrix, the second function adds the snake to the matrix, the third function adds the apple, and the fourth function adds a crash, if there is supposed to be any crash. So again, these are sort of immutable methods in order to just to keep my head straight in this. So matrix.make, we can see up here, right? The matrix.make, here I called it table and not state, because a table is anything that has columns and rows. But I mean, actually what we will pass is, we will actually pass the state, but since we only care about the columns and the rows, I figured I'd call it table here. And what make does is essentially that we use this helper function rep, right? So if we look at the base library, const rep, here we have the implementation of rep, and what rep does is that it takes a constant and then it takes an n, and then it maps this constant using the function k, which is the const function, over the range from 0 to n. So this sounds a bit bonkers, but what this actually means is that if you have, actually let's jump into Node and let's look at this. So const base is require, right, and then we have the base library, and then we can say base dot rep, and if I say a and then I'll pass 10, you can see that we get 10 A's. If I get past 3, we'll get 3 A's, right? And if I, instead of A, if I have 1 here, I'll essentially get an array with this thing repeated the number of times as the second argument that we're passing. And rep was implemented in terms of range, and what range does is just that, let's see if I can remember the syntax. If we do this, Right, then we get a range from 10 to 20. We get an array of all the elements of 10 to 20. So what we were doing is that we were mapping over that range in order to have an array of multiple elements. And what we were mapping is that we were mapping the function k of the constant that we were passing. So when we did base.rep a10 here up in the beginning, for example, then our constant is a. So if I say k of a, then I have, base.k, then I have a function that accepts an argument, but it doesn't care about which argument it's passed. Regardless of what argument is passed, it's going to respond with a. And that's how we can, when we map, so actually let's do that manually. Like if I have that range from 10 to 20, and then I map over that, and if I map k of a, we will replace, base k in, base.k, we will replace all of the values in the array with a. And that is essentially the way that rep works, and I guess range and k as well, and map. But anyways, so that's why we do rep here. So I think it's pretty interesting. I mean, what we do is we repeat the repetition of period, or the string period, over the number of columns that we have in this table. We do that for every row that we have in this table. So that's a pretty concise implementation of making a two-dimensional array filled with dots, right? So that's the first thing we do. We make the matrix based on the state. We make the matrix from the state. But then here we have these three functions that we want to use to add additional things to this matrix. We want to we want to adjust particular cells in this matrix. And note how we're passing state to these, because essentially this one only requires the state to be passed once, but these actually require the state to be passed twice. So we'll invoke them like this. So add snake is a method that can be defined only when we know what the state is. And this, I mean, I was struggling a bit with this. I think this didn't turn out super nice. So if you have any suggestions of how to rewrite this properly, super interesting if you want to post anything about that. I was toying with the idea of probably using the S combinator or converge or something along these lines. But probably we could find out more sensible ways of expressing this. But anyways, what we do essentially is, so add snake, what it does is that when given some state, it will produce a function that's essentially a pipeline where we spread the mapping of setting x, or rather I should say spread the result of mapping the value x over the snake. So essentially, let's think about it. I mean, this looks a bit hairy, but actually it's not that strange. I mean, so the thing about it, like the snake in the state is an array. It's an array of positions. So what we do is that we map the function of setting x, and setting x in the matrix takes a particular position. And so by mapping that, we get a list of functions that we then spread over this piping. So we spread it into arguments. So we make a function that when passed a state, will run that state, not when passed a state, when passed a matrix, will run that matrix through a bunch of matrix.set transformations that sets x at that particular position. And if you look at set, I mean, set is also fairly straightforward. What it does is that it takes a value and then it takes a position. And what it does then, so the position is then a point, right? Maybe I should have said point. So something that has an x and y. And it calls adjust on the y, or adjust at the y position, but then passes the adjustment of the x position of the constant of the value. So what we do, if we express this in a less strange manner, actually, what this is that we're saying, if we would do this in a mutating fashion, what it does is that it takes another argument because it's point free, right? So it also takes the matrix. And what we do is that we say the matrix of position y and then position x is equal to the value, and then we return the matrix, and then we return the matrix. So that's essentially what the set method, what the set function does. But now we're mutating, and so now we're trying to do that without mutating. And when doing that, we also got rid of the matrix variable here. And of course, adjust is a function that we defined here in our base helper library. But of course, it's also available in a lot of different libraries. And what adjust does is simply that it takes an n, which is an index, it takes a function, and then it takes some kind of collection, some x's. And what it does is that it runs the function at the index n of the x's, right? So it's a way of, if we go back here, right? Like if we say list index equals value, or more specifically, if we say function over, if we run a function over the value at that index, right? That's what this version of adjust does. And then we pass k here because we're not actually interested in running a function over the value. We don't care about the old value. We just want to replace it with a new value. So that's kind of a general version of adjust. And yes, so this we do in order to so essentially what set does is that when given a value, when given a position, and when given a matrix, it produces a new matrix that looks like the old matrix, but where the value at the position has been updated to the new value. And that's essentially what we do with set, right? And so that's why we use it in add snake, and we also use it in add apple, and actually not add crash, because here we did a more simple implementation, I guess. But yeah, that's how we use it in add snake. The way we use it in add apple is much more simple, much more simple. Then we just simply say matrix.set, and we set to an O at the position of the apple, right? So state.apple contains a position, and we're just saying matrix.set at that particular position, right? So, I mean, this we could change to an A, and then if we run, you can see that we now have A's instead of O's that represent the apple. So that's the apple. And then the crash is very simple. Here we just say that, okay, if the snake length is 0, in other words, if we don't have a snake, if we've crashed or if we just started the game, then we map the mapping of the constant dash. So over this grid, think about it, the grid is a list of lists. So over every column or row, depending on which order we structured it, I think maybe it's row. So over every row we map, but we map the function that is the mapping of every column. And over that we map the function k, which is constant, that returns, regardless of what it gets, returns whatever we passed it. And what we passed it in this case happens to be this dash symbol, or this pound sign, this hashtag. And that's only what we do if we don't have a snake, so if we've crashed. But if we hadn't crashed, then we pass ID. And why do we pass ID? Because ID is the identity function. So that means that, well, if we haven't crashed, then the grid needs to stay the same. If we didn't do that, let's say we did this in both of the cases. So instead of doing ID, we do this mapping again, then it'd be a constant crash. Like it looks like constant, but we're actually just redrawing this constant and recomputing this constant all the time. But yeah, so that's why we need to pass the ID. And if we didn't do this mapping of pound, that wouldn't be the end of the world. It would just not be obvious when we've crashed. So what we want to do is visualize, like we did in the web, right? Like here, when we crash, we have the screen sort of turns red like that, right? And here in the terminal, we want every position to be replaced by a dash. And that's that, right? So these are the matrix operations that we have. We can make a matrix, we can set something in the matrix, we can, given some state, produce a function that, when given a matrix, adds that snake to the matrix. Similarly for the apple, and similarly for a crash. And then we can take a matrix and turn it into a representable string. And then here we have the from state function that essentially first makes a matrix, adds a snake, adds an apple, and adds a crash, all in order, so that we can simply just call that from over here in our game loop when we want to show. Okay, that's show. Then we also have step, but step is super trivial. Similarly, if we go up here into the top, like similarly to the web, right? Like if we go back to web.html, you can, so web.js, you can see here in the top that we have this mutable state, where we say that the state is equal to initial state. For some reason I chose lowercase s and uppercase s here. That makes no sense. But in the CLI here, we have a variable called state, which starts as the initial state from the snake, and that is the mutable state. And the reason that that's mutable is, of course, that we need to listen to these key events. So I'm not gonna bother you about how this listening to keys work, but this seems to be like the way we do it in Node when we want to listen to key presses. So we capture what's in standard in, and if we happen to press Control C, we need to exit the process because people need to be able to exit the program. But if not, then I'll just do to upper on it, so we don't have to worry about lowercase w or uppercase w, and then we just look for WASD as in the web case, right? And HJKL, and we look for up, left, down, right arrows. And what we do is actually the same thing. Let's look at this. So yeah, so the state is equal to the enqueuing of the old state and the new move, and then we break. And this is the same thing as we had here in the web, where we said, okay, enqueue based on the new state this new move, and compute a new state from that, and replace the mutable state with this new state that's computed. And that's the way we do that. And yeah, I guess that's pretty much it. So to do that read line, we needed to read in the base node library read line. It seems that there are other ways of doing it, but this seems to be the easiest way. So yeah, it kind of seems like that's it. It seems like a lot of code in some sense, right? But if you think about it, what I would argue is that what we've done is that the snake implementation is actually only this file. It's actually only snake.js. Like this is the implementation of Snake. The other stuff regards how to display the Snake game, like what graphics version or engine you want to use your Snake with, what GUI you want to use your Snake game with. So which way you want to display Snake to the user, and which way you want the user to interact with your Snake game. So again, like if we think broader than game programming, functional programming is really susceptible to modularity. And so what I mean is, when you produce small functions, you can really quickly feel how they become very composable and very reusable. But yeah, I mean, but if you actually know exactly what you're building and you know that you're not expecting any change and you have a strict specification, then yeah, maybe you don't need to be worried about change. But if you are worried about change, like if you're building an application that might change over time, or if you're building something that might be shipped to multiple platforms, then approaching something even like game programming, kind of like we've been approaching it today, I think actually makes a ton of sense. What do you think? Let me know in the comments and let's discuss. Beyond that, if you thought this was interesting and if you want me to decompose any other games, let me know, like Tetris or Pong or whatever. I mean, shoot something in the comments. Either way, clearly this code can be improved a lot, but hopefully you find something useful as we dove through this piece of code. Thank you super much for watching, and I'll now resort to playing some Snake. I'll see you in the next one.